Learn the fundamentals of composites as they pertain to aeronautics and high-performance industries. Your instructor, Dr. Lin, is a professor in the William E. Boeing Department of Aeronautics and Astronautics at the University of Washington, and an expert in the design and analysis of composites for the airplane industry. Composites are used in many industries today to manufacture high-performance products at an economic advantage. These industries range from space to snowboarding and include manufactured products for aircraft, transportation, energy, construction, sports, marine, and medical use. There are many material, economic, and aesthetic advantages to using composites for high-performance products.
From structural applications point of view, we design composite because we want to increase the strength, stiffness, and also reduce weight.
Solid knowledge of the physical and mechanical properties, tooling, design, inspection, and repair is recommended for working in this medium.
Has different properties in different directions. So when you design composite structures, you don't just use zero because it becomes very weak in the other direction. So you have to put some fibers in this direction, some prepreg plies in that direction. That's called 90. And then you put another direction, that's 45, 45 minus 45.
Your role in this course is paramount. Successful participation in this online course means a commitment to watching short videos, completing quizzes, and engaging in the discussion forums associated with the content material. We are excited to have you along for the experience. We hope the course is challenging enough to hold your attention and accessible enough to enable your mastery of the skills and knowledge that are provided. Let's get started.
Polymer composites, or fiber-reinforced plastics as they are commonly known, is a new class of advanced materials which are different in many aspects from the traditional materials such as metals, ceramics, or plastics. They are made in such a way that they provide extremely high strength with sufficient stiffness and toughness with light weight. This combination of properties offer great advantage in mechanical design. By definition, a composite is a material in which one material which acts as matrix is mixed with one or more materials acting as fillers, with the purpose of increasing strength and other mechanical properties, but reducing the overall density of this new material. The matrix and the filler are chemically different, and there is no chemical reaction between them, but they form good bonding between them. This interfacial bonding may be enhanced by some chemical or physical treatment of the fibers. Though the concept of composite material is very old, going back to the antiquity, the modern plastics-based composites were developed in 1930s. This class of material was originally developed by the company Owen Corning in the USA, and this type of composites are known as fiberglass. They contain chopped or continuous strands of glass fiber with matrix of epoxy or other polymers. However, as of today, there are many types of fibers and matrix polymers used for advanced composites. The biggest impact of the use of advanced composites can be seen in the aircraft industry. Today, much of the efficiency and load bearing of aircraft can be credited to the use of carbon fiber epoxy composites. These are the lightest and strongest materials available. In the passenger aircrafts were used from 1970s. For example, in Boeing 747, the jumbo jets, the percentage of composites used was 1%. This increased to 11% by weight in Boeing 777, and for Boeing 787, the Dreamliner, about 50% of material is by weight is composite. Carbon fiber epoxy composites are used as structural materials for the fuselage, wings, tail, doors, and much of the interior. Lightweight composites enhance an aircraft's efficiency in load carrying capacity and huge advantage in fuel saving. In fact, the very first large-scale use of carbon fiber epoxy composite was the Boeing Sikorsky helicopter, in which 60% by weight was this composite. Started in 1991, this helicopter was designed as a stealth and attack helicopter for the US Army. However, because of the long delay, budget overrun, and the end of the Cold War, the helicopter project was terminated in 2004. The Airbus A380 also uses fiber reinforced composites for many of its parts, though the fuselage is still of metallic type. A380 uses carbon fiber reinforced plastics for wing ribs, upper deck floor beams, and center wing box, landing gear doors, unpressurized fuselage, vertical and horizontal tail plane, tail cone, engine cowlings, flap track panel, and much of the interiors. Look inside of any airplane and you will find the interior is mostly plastics or composites. This reduces the weight of the plane and hence adds to the fuel efficiency. FRPs are already being used in many sports and high-end cars. Full body is made with carbon fiber epoxy composites. They save weight without compromising on strength and safety. Many years ago, I had come across an accident site where a sports car had collided with the guardrails on the roadside. The car had composite body and I could find many broken pieces as far as about 30 meters from the accident site. The failure of these composites is not of ductile type, but it has huge amount of toughness due to the different failure mechanism of composite materials than that of the ductile materials. The broken pieces appear to be made of hybrid carbon and glass fiber with epoxy as the matrix. These pieces break in a very characteristic brittle type of fracture. However, before they fracture, they absorb much of the energy and therefore they are very tough materials. Here also we can see that the material has broken without much of ductility. In this piece we can see the inside of the composite material. So it appears to be a mixture of carbon fiber and glass fiber with epoxy as the matrix. So the white part is glass fiber, the black part is carbon fiber, and epoxy is used as the matrix. Energy sector is also utilizing composites in a big way. As we are making machines bigger, lightness without compromising on mechanical performance is an asset. Today, wind turbine blades are ever increasing in length. There are turbines with blades as long as 100 meters. The length of the largest airplane is about 84 meters, and airplane's one wing length is about 54 meters. With such a huge size of the machine, which needs to stay at a height of approximately 260 meters, it is absolutely necessary that these turbine blades are as light as possible, but they also must be strong against wind power. They should be tough against impact loading such as strong wind and must withstand all kinds of weathers, cold, heat, rain, sea environment, etc. Carbon fiber and glass fiber are used with epoxy polymer to make such huge mechanical items. The other energy sector that urgently needs FRPs is the hydrogen gas-based energy production. One of the challenges in this field is the storage of H2 gas, which is quite damaging for metals such as steel because of hydrogen embrittlement. Also, for any mobile energy solution such as for automotive application, it is necessary that the storage tank is very light, not a bulky steel cylinder. This is solved by having FRPs as the materials for hydrogen storage tank or cylinders. With extremely high strength and toughness, a cylinder made of FRPs is able to store the gas at very high pressure but with safety. Sports have in general benefited immensely from advanced materials such as FRPs. For example, a racing bicycle can be made very light by using carbon fiber epoxy composites instead of steel or aluminum frames. A lighter bicycle will be easier to ride in a race, rowing, or any kind of water sport depends on materials that are strong, stiff, and light. Often glass fiber or carbon fiber based plastic composites are used for making the boats, oars, and any kind of floating boats, etc. Today,